Let's continue our discussion on decision trees. In this section, we are going to focus on tree building and pruning. We discussed the key differences of decision trees versus regression, so you should pay attention when you have your own data and select the proper methodologies. And in this section, let's discuss tree building and pruning process. The tree building process is we're trying to divide the predictor or independent variable space into different regions. That is a set of possible values for x1 all the way to xp into j distinct and non-overlapping regions of R1, R2 all the way to Rj. Remember in a toy example that we had, that we have x variables versus y, we have 3 different regions, and in there we only have one independent variable, that is x. We divide based on that x into 3 distinct and non-overlapping regions. But in this case, when we have more independent variables, p-dimensional, x1 all the way to xp, and then we're still having that idea to divide all those p-dimensional axes into distinct and non-overlapping regions of j different regions. And then for every observation that falls into the region Rj, we make the same prediction, which is simply the mean of the response value of the training observations in region J. So we have 3 different regions, and then for each region, we use a mean for each one of those observations that's actually in that region. So in tree building process, we're just aiming to divide the whole space, independent variable space, into different regions. In theory, the regions could have any shape. However, we choose to divide the predictor space into high-dimensional rectangles or boxes for simplicity and for ease to interpretation of the resulting predictive model. So just remember that we're aiming to divide the predictor space into high-dimensional rectangles or boxes. The goal is to find the boxes of R1 all the way to Rj that minimize a function of fMSE, given by this equation. So what is this equation? It is a function of k and tk here, and k is the variable that you picked. Tk is a function, tk is the threshold that you picked. If you remember that toy example, this k essentially is at x. Tk for first split is 5. And then this cost function has 2 components. The first component is a function of MSE on the left, and the second component is a function of MSE to the right. And then what is MSE? MSE is first of all, we need to look at it's a difference between the predicted value minus each individual observation squared and summation, right? And then this prediction itself is for all the node that's in this box, what's the corresponding y value, sum of them together, divided by number of nodes, number of observations in this node, which is m node. So essentially the average of all the observations in this region, and then use this average minus each individual observations and then squared, and then sum all of them together. That would be your MSE for that node. So in other words, if you look at just one particular branch or one split, this is a weighted average of the MSE on the left side versus and the MSE on the right side, weighted average of those 2. This is our function. But overall, we're trying to minimize this cost function of all the leaf nodes at the end of the algorithm. And again, this Y node estimate is a mean response for the training observations within the specific box or node. We first select the predictor xj, or let's call it k, and the cut point, which is a tk, such that splitting the predictor space into the regions, if just one variable, then just this x given that k is less than tk versus k is larger than tk. Of course, if it's more than one dimension, then it's still the same thing, just the x given that this particular xj or k is less than that threshold of tk versus larger than equal to that threshold of tk, leads to the greatest possible reduction of that j, that function. So in other words, if you look at the root node, you know what is your function j, k, and tk, and then you want to find a predictor variable that a predictor variable and a threshold that can have the biggest reduction of your j function. Because if we have so many different variables to choose from, and if we have all kinds of thresholds that you can choose from, you have to pick one of them to split the root node. So the objective is to find a variable and threshold that would be able to have the greatest possible reduction of your j function comparing to your root node. Okay, we can do the same thing. Repeat the process, looking for the best predictor and best cut point in order to split the data further so as to minimize this j, k, tk function that we just defined within each of the resulting regions. As you can see here, right, every single node, I'm trying to make a decision to see which variable I should pick, which threshold I should be using. Okay, so however, as time goes on, you can see instead of splitting the entire predictor space, we split one of the two previously identified regions so that we have three regions for the second step. Right, first step, you just have one node, split it to two, and then you pick one of them and split to two as well so that you have three regions. Continue to do this, trying to minimize the j function, and the process continues until a stopping criteria is reached. For instance, we may continue until no region contains more than 5 observations. This would be one of the stopping criteria, just one of them. So now you got the idea of how this tree building process is working and how the tree is constructed. Unfortunately, it is computationally infeasible to consider every possible partition of the feature space into J boxes. You already see the complexity of the problem, right? If you have a lot of independent variables and you have a lot of different thresholds that you can choose from, then computationally, it's very expensive. So for this reason, we take a top-down greedy approach that is known as recursive binary splitting. And then the approach is top-down because it begins at the top of the tree and then successfully splits the predictor space. Each split is indicated by 2 new branches further down on the tree. It is greedy because at each step of the tree building process, the best split is made at that particular step, rather than looking ahead and picking a split that will lead to a better tree in some future step. So I cannot look a couple of branches down to make a decision. I can only think about this node, just one split, one branch at a time. That's why it's greedy, and it's not going to generate global optimal solution. It would only can generate a local optimal solution. Once we are able to identify all the regions, we can use the average to do the predictions. The average of all the operations belong to this specific box or region. And here, yeah, that's that. Yeah, and next we want to discuss is how to pruning a tree. So the process described above of the tree building process may produce a good prediction on the training set, but it is likely to overfit the data, leading to poor test set performance. Why is that? Why is it possible that we're going to overfit the data? If you think about it, if we don't have any stopping criteria, if we continue to do this, we are able to differentiate each individual observation to a leaf node. Think about this one more time, what I just mentioned. You are able to continue to divide the tree so that you're able to have each individual observation be one of your leaf nodes. We can continue to split. Instead of 3 levels that we saw in the toy example, we could continue to split all the way through so that at the end, each individual observation would be one of your leaf node. That's definitely possible, because if this observation is between 4.5 and 4.8 being X, then you would be able to differentiate it, right? The other one is 4.51, the other one is 4.81 to 4.9, then it's another observation. The next one is 4.89 to 4.92, then you would be able to differentiate it as well, right? So at the end of the day, you would be able to have all the leaf nodes being each individual one of the observations, then you're overfitting the data, because you would have a gigantic tree, even for a toy example, so that you would be able, at the end, it's definitely going to overfit your data. And a smaller tree with fewer splits, fewer regions R1 all the way to Rj, might lead to a lower variance and better interpretation of the cost of a little bias. So if you recall, what is a bias? Bias is how your model is doing on your training data set, and variance is how your model is doing on the data that you have not seen. So you want to make sure that your model is doing well on both, right? So you don't really want to say, I want to build the best model that's gets a minimized MSE for my training data set. That's not the purpose. The best model should be a balance between doing well on the training data set, also doing well on the testing data set, the data that you're not seeing yet. So we're trying to have this balance. If your tree is smaller, it's probably not doing so well on your training data set, but it would be easily generalized to some other data set as well, then it's a good model. In decision tree scenario, we want a smaller tree. It may have lower variance for unseen data, but potentially you have a cost to have higher bias. So one possible alternative to do that is to grow the tree only so long as a decrease in the J due to each split exceeds some high threshold. So you would stop with that, because if you continue to split, you would be able to decrease this J almost to zero. But you can't. It's just because of the overfitting issue, you don't want to continue to split. If you preset a threshold of J, that reduction of that objective function, then you could stop at some point. This strategy will result in a smaller trees, but it's too short-sighted, meaning a seemingly worthless split early on the tree might be followed by a very good split. That's greedy issue, local optimization problem that we just discussed. That is, a split that leads to a larger reduction in J later on is actually not being considered. Potentially, so to see, essentially saying that early in the process, you thought you found a good split, but really it's a local optimum. It's not that great, because later on you even find a better split down in the tree. However, just because of design of the algorithm itself, it's greedy algorithm, you would not be able to get away from that. And then a better strategy is something called pruning. What you do is you start with is growing a very large tree T0 and then prune it back in order to obtain a subtree. So instead of starting just growing your tree without considering anything, that strategy is kind of greedy without achieving optimal solution. Here, a better solution would be start with a very large tree T0 and then prune it back in order to obtain a subtree. Of course, cost complexity pruning, also known as something called weakest link pruning, is used to do this. So which link you want to prune, throw away, basically. Let's use this example. We consider a sequence of trees indexed by a non-negative tuning parameter alpha. For each value of the alpha, they're corresponding to a subtree of t, which belongs to t0, such that we want to calculate this summation not only on the MSE, but also give an alpha absolute value of t. So this is together. We want to make sure this summation quantity is as small as possible. Here, t absolute value indicates the number of terminal nodes of the tree t. Remember, t is a subset of t0. And Rm is a rectangle. This is a rectangle, is a subset of the predictor space corresponding to the mth terminal node. And y estimate node is the mean of the training observations in Rm. So we have a subtree, and then in this tree, we calculate those quantities, and then we want to make sure this is as small as possible, so that we pick the best tree among all the subtrees of T0. Okay, if you think about this one more time, it's really a gigantic tree, and then you want to pick some subtree with the consideration of the number of terminal nodes, with penalization of the number of nodes in the tree. And then meanwhile, you want to minimize this MSE kind of metric. So it's more of a regularization parameter. Alpha itself is a hyperparameter you can adjust. T is really the tree size, and so that you would be able to find your the tree that's better, the best actually. So the tuning parameter alpha controls the trade-off between the subtree's complexity and its fit to the training data, and we select an optimal value of alpha hat using cross-validation, and then return to the full data set and obtain the subtree corresponding to the alpha estimate. That's something called pruning a tree. That's the best possible solution for decision trees to find the best tree. So here is a summary of the algorithm. You use recursively binary split to grow a large tree on the training data, stopping only when each terminal node has fewer than some minimum number of observations. And then you apply cost complexity pruning to the large tree in order to obtain a sequence of best subtrees as a function of alpha. And then you use k-fold cross-validation to choose that alpha. For each k, ranging from 1 all the way to k, repeat step 1 and 2 on the 1 to k1's fraction of the training data, excluding the k fold, and evaluate the mean squared prediction error on the data in the left out k-th fold as a function of alpha, and then average the results, pick the alpha to minimize the average error. And now you return to the subtree from step 2 that corresponds to the chosen value of alpha to pick that tree. So this is a tree building and pruning algorithm, which I don't think the textbook actually had a lot of detailed discussion. If you are interested in, you should definitely go through. So think about what are the regularization hyperparameters that we can consider, especially in scikit-learn. It would be this, for example, max steps, how many layers you want to split. You have to stop somewhere, right? You could, for example, in the toy example, we only have max steps would be 2 because start from 0, step 1, step 2. And the minimum sample split, the minimum number of samples a node must have before it can split. If it's less than 10, I'll stop. I'm not going to continue to split. Min sample leaf, the minimum number of samples a leaf node must have. The terminal node or leaf node must at least have 10 samples, for example. As I mentioned, if you only have 1, if you don't have this min sample leaf, then it would continue to split the tree into each individual observation would be 1 leaf node. And the mean weight fraction of leaf, same as min sample leaf, except it is represented as a fraction. Max leaf nodes and max features. These are the regularization parameters you can adjust in your scikit-learn command or function that helps you to regularize your decision tree. So here, this is example from regression tree. You can use scikit-learn.tree import decision tree regressor, and then use max steps equal to 2 to fit a regression tree. The data here used is from iris data, and iris data only take the third and the fourth column, which turns out to be petal width and petal length. And then there, if you look at this this first split, which is says x1 is less than or equal to 0.197, and then if it's true, you get a new node, else you get the node on the right-hand side. And the MSE of the original sample is this, meaning if I use all the observations average to be my prediction and calculate what's the corresponding mean squared error, I would get MSE being this. And it has 200 observations. And this is my Y node estimate. If you think about the jargon that we used earlier, this is a Y node estimate for this node. Once we split, I say, okay, all the observations less than for x1 less than or equal to 0.197. What are all those nodes? And then among those nodes, I can calculate all the MSEs and its sample. So if you pay attention, we have 200 samples. We split on the left-hand side 44, right-hand side 156. Same thing for this 44, it can be further split to 20 and 24. And then one more thing I want you to pay attention here is, this is MSE, original MSE, 0.098. And then here, this MSE plus this MSE, roughly, I'm not talking about the exact calculation because there's a weight there, right? We didn't discuss that weight here, but you could, which is, it should be equal to 44 divided by 200 times 0.038 plus 156 divided by 200 times 0.074 is much less than the original function, which is 0.098. So the purpose of this split is just trying to minimize that quantity and find the best split and the best variable. So this is one example here. It's as simple as this command that we just show here, but it's something that you should definitely try to understand. What is that output? How do I interpret that output? And then it would be different from R, look different, but it's all the same metrics that you would be using. So this is from Python. And then let's use the same data that we just mentioned, that tree. You can see that the first split is really coming from here, which is around, what we say, around 0.197, so around 0.2. And then on the left-hand side, which is use 0.092, which is 0.1, as another split. On the right-hand side, use around 0.8 to be the second split. So this is the first level. Depth 0 is really differentiation between here versus here. And the depth 1 have two nodes. That's why one of them is this. Second one is really this versus this. And then what you do is you use all the observations. So now you have different regions, region 1, 2, 3, 4. And then you use the average of each region to be your Y estimate. Now, this just shows you that what's on the left-hand side, you use max depth equal to 2. And what's on the right-hand side, you use max depth equal to 3. Apparently, you see that on the right-hand side, it has more predicted values. If you continue to think through this, right, if I have max depth is equal to 300, what would happen? It would be 300 different regions, right? And then if my observation is really only 200, right? If I use max depth equal to 200, each individual observations will be one specific region. And then it's apparently would be overfitting the data, just because you would be able to predict the Y 100% correctly for each individual observation. That's the reason we want to use max depths or the minimum number of leaf nodes, minimum max number of features, all those regularization parameters to adjust your regression tree. So this is exactly what I just mentioned. If you have a minimum samples leaf equal to 10 on the right-hand side, that's a tree look like, which says in each region at least have around 10, more than 10 observations. Versus if you don't have a restriction on the left-hand side, you can see that fit is almost like overfitting your data. The fit is wiggling and trying very hard to fit each individual observation. What we're after is what we saw on the right-hand side. By adjusting regularization parameters, of course, you have multiple regularization parameters that you can adjust to find a tree that would do reasonably well on your training data set, and we know it's going to do reasonably well on the tested data set as well. Okay, that concludes our discussion on building trees and tree pruning process in decision tree, to be specifically decision tree regression models. Okay, I'll stop here and thank you.